Third part, I'll talk about how to clean the microscope. I'll show you some tricks with the cover glass. We talk about measuring with the microscope, and we will train the plasma of some cells of a red onion to contract and to expand as we want it. From time to time you have to clean the lenses. Let's remove this dust cover. Both the object lenses as well as the eyepiece. There will be pieces of dust, or in case of the eyepieces there may be a greasy residue because your eyelashes have touched the lenses quite often, or you simply haven't been careful enough and well, yes, your object lenses have touched the glass, the slides or cover glasses, or even you have dipped the object lenses into some kind of liquid. Because dust is everywhere and always, you should, of course, always use the dust cover when you are not using the microscope. And please remove object lenses, if possible, and eyepieces only for the shortest possible time to prevent dust from coming into the optical path of your instrument. Okay. If you have to deal with dust only, you can use the same equipment you use for cleaning the lenses of your camera. So cloth like that, or instruments, small instruments like these. You can also use a paintbrush, a very soft paintbrush, but please make it free from grease before you use it, and then after that it should be dry before you go and clean your lenses. If there is still some kind of dirt left and you need some, well, let's say, stronger weapons to remove it, try using some water with a drop of dishwashing liquid. But do not use detergents you use in your dishwasher. These detergents are very aggressive and they may do harm to your lenses. Yes, and then of course water and soft cloth or a brush. Never ever, and now it's very important, never ever use any kind of alcohol, because alcohol destroys the coating of your lenses, and so please don't use detergents meant for cleaning your windows, because they mainly contain alcohol as well. Don't do these things. You may use white gas, which is meant for purposes of cleaning only, like that here, but take care, be very careful, because it's highly flammable, and don't inhale the fumes. They damage your health seriously. Okay, yeah, all right. I'd like to tell you about an experiment I made recently. There was some dust in this lens tube, and I had to remove it, but the optic sits deep in the lens tube and I could not reach it. So I constructed that. I thought of using a hoover, and I removed this brush from this piece and adapted a hose from the cellar. I cleaned it, of course, before using it, and well, combined these two pieces by using something my granddaughter gave me a piece of her balloon. All right, and I have to say, it worked great, it worked fantastic. It removed all the dust, it sucked the dust out, off from the lens and out of this tube. And it worked also great with this USB lens. But I tell you something. It caused nearly a kind of, let's say, a small catastrophe when I tried to use this construction here, the Hoover, cleaning this eyepiece. The problem was that this eyepiece here consists of two lenses, one here in front and one here at the end. And by using the vacuum cleaner from this side, dust was sucked out of the air through the mechanics of this lens into this eyepiece. So there was dust between the lenses. I had to unscrew it. I do it now. Don't do it at home if it's not necessary. And you see, here is the first lens and here is the second one. Put it at once together so that no new dust will come into it. And I had to clean both lenses from both sides, and it was a terrible work to do. It's not so easy. Very fine. Oh, well, here it is. So, the result of my experiment with this construction is a little bit ambivalent, as you know now. I will always use it for cleaning this tube. I will probably also use it for cleaning this USB lens, but I won't ever use it for cleaning anything else of this microscope. Those of you who have watched my video about life in a drop of water, part 2 of this series, may have asked themselves, how big are all these creatures? Well, there are special eyepieces for measuring length, but they cost money. I have seen prices between 90 and 200 bucks. As I don't want to spend more money at the moment, I have come up with the following method. It doesn't lead to an exact result, but you can get an approximate result that gives you, well, a good imagination how big the things really are, the things you are observing. All right. At first, I opened my spreadsheet, formatted the columns with border lines, and adjusted the width of the columns to 0.02 centimeter. Then I printed the sheet using a laser printer and cut a sufficient piece off the printout. Then I took an adhesive tape and fixed my self-made scale on a slide. The whole scale is 2 millimeter wide. The paper lets enough light through to make out the lines. Well, now I can measure the diameter of the field of vision depending on what object lens and eyepiece combination I am using. This one, for example, or this one. With different eyepieces, I get, of course, different diameters of the field of vision. But now, using the USB lens, just a moment, you can get some quite interesting and very useful results. Let's start the capture to show you. Oh, other way around. So, yeah. You can make out the lines. You see we are not talking about exact measuring, but what is quite easily to be seen is that with the actual factor of magnification, it's the smallest lens with the factor of object lens with a factor 4. The width of the screen here is nearly 2 millimeters. So the screen is 2. The picture here is, the recording is always 2 millimeter wide. So, and the resolution of the picture I always work with is 1280 times 1024 pixels. And that means that a length of 1280 pixels horizontal in the picture corresponds to a real length of 2 millimeter under the microscope. So 1 pixel in the picture corresponds to 1.5625 micrometer. All in all, I've got the following relationships with the data of lens 3, magnification of 60 times, not being measured but deducted from the data of lenses 1 and 2. Knowing how many micrometers correspond to 1 pixel is very helpful, because there is a software to show you the length of an object in a picture in pixels. I use the software Axiovision by the German company Zeiss. They offer a light version completely for free. You can download this version from the website you will find in the descriptions to this video, respective in the comments. To give you an example, let's look at the following picture. The measured object is about 28 micrometer long. Those of you who are the proud owners of a microscope equipped with the vernier scale can, of course, measure the diameter of the field of vision more precisely. And as the slide stage of my microscope is equipped with 2 of such scales, one here and one here. Let me use them now and compare the results with those achieved by using my self-made spreadsheet scale. The biggest disadvantage of my self-made scale is the missing of clearly and well-defined lines. The lines of my scale are somewhat blurred. Those of you who have seen the first part of this series may remember the leg of the housefly. I'm going to use the end of the claw as a point of reference. Then I use my vernier scale and read off the distance from the left border of the field of vision to the right border. Because I don't want to extend this video too much, you will find an explanation how to use a vernier scale on my website and not in this video. Please see the comments to this video to find my website. I have done all the measuring already, and now let's compare the results. Let's have a look at my spreadsheet. The results of both methods accord with each other so well that I have decided to use the arithmetic average in my further videos. So the figures and numbers printed in blue. Well, the onion red one. The first thing we have to do is to remove the dry outer leaf.
through. Okay. Okay. It should be enough, but to make it a little bit more beautiful, let's remove them all. Yeah, okay. Alright. Let's throw it away. Okay. The next thing, I will need a scalpel and tweezers, not these ones, these ones, and a scalpel. Definitely that one. Yeah, okay. Perhaps I need this one as well. I'm not so sure if I'll manage to do what I want to do, what I'm going to do at once, because it's only the second time. So let me try to take the outer skin. I don't know, perhaps it's already enough. Well, perhaps it's already enough. Alright, let me have a look. Sufficient to show you perhaps a little bit more. Let's try different technique. We cut a rectangle. Yeah, a rectangle. Perhaps even one more rectangle, and perhaps even a third one, deeper here. I don't know if this is the most professional technique, but I'll try it nevertheless. And yeah, I think it's okay with this scalpel. I cut these from the skin from it. Yeah, here we are. Yeah, okay, alright.
Alright, so a small piece of onion skin, and I'll put a drop of water on it. Alright, alright, and a cover glass. And let's have a look at it. Alright. Okay, here we see it. Yeah. The cells with the red plasma. Let's find a nice part of it. Here. Okay, so now let's, or what's the other side? Ah, perhaps it's even better. This side, yeah. That's better, I think. So now let's observe this part of the skin, and let's look what happens when I put a drop of a saturated solution of simple kitchen salt under the cover glass. I put the drop next to the cover glass. Here should be enough. And we see at once the red plasma starts to contract. Yeah, I'll take these stripes of coffee filter. No, it's nearly not necessary. To pull the saturated solution of kitchen salt under the slide by sucking out the water, what is under the slide. It should make the process a little bit faster, but it's not necessary, I see. By the way, while doing so, using these pieces of filter to pull liquid under the cover glass, be careful not to touch the cover glass. It would, of course, change the picture you are watching. Okay, but in between, the red plasma has contracted all over the place, and I think it's time to reverse this process. Now I'll suck away the salt solution. Need some more filter stripes because the next step is replacing the salt solution, the solution of kitchen salt, which is now under the cover glass and on the onion skin. To replace it, I want to replace it by, All right, so I want to put clear water under it again. Oh, but I have to close this. So don't change the pipettes. This is the pipette for clear water. So placing clear water under it. Yeah, the water is going under the cover slide already. You saw it on the picture. And hey, you see? Well, that's better. The red plasma is getting bigger and bigger again, so until it will fill the whole cell. You see, on the edges, where the clear water comes in first, the red plasma has already expanded completely. So let's continue the thing with the water. No, let's at first put some more water on it. Okay. All over the place, contracted plasma. Only on the edges. Here at the edge, where the clear water came in first. It's expanded again. I'll do something else. Drastical. It's definitely not the way it should be done, but I'll take the cover glass away, take my pipette and put a lot of pure water in. And perhaps you can see it, I hope at least, now that this, even with bare eyes, that this sample here is nearly white. So it has lost its red color it had before. So now let's put clear water on it and a new cover glass. The process, for example, I don't know if I have told you already, is called plasmolysis, when the cells lose water and the plasma contracts, and deplasmolysis the other way around, when water is coming into the cells again and the plasma can expand. But I think it's expanding slowly. Yeah, okay, yes it is. Yeah, so I'm happy that I could show you, and I'm happy that I could see it again. I did it once, I told you already, and it worked out nicely. It's a little bit, it's quite slowly, but it's expanding here. I see it expand. Yeah, the circles are getting bigger. Let's give it some more time. Yeah, now it's clear. It is expanding. Here, at the edge, you can see it. Nearly, it has reached the border of the cells, the cell membrane already. Okay, and now it's expanding the other way, up and down. Okay. Yeah, let's watch this cell here. I think that's the most interesting thing going on. Yeah, what about my water? Yeah, there's still enough water. Let's the process go on for a while, and I will use the time in between to explain to you what had been going on while the red color, the red plasma of the cells contracted, and what is going on right now. The picture shows a cell with the red cell plasma full of water molecules and the cell wall. Now, if the same number of particles, for example 12, bump against the cell wall from both sides, from above and from under the cell wall, there will be 12 molecules of water bumping against the cell wall from above, but only 3 from below the membrane. The other 9 particles bumping against the cell wall from below will be crystals of kitchen salt. But the cell wall cannot be passed by such huge particles like crystals of kitchen salt, but it can be passed by the small molecules of water. So, the result, there will be 12 minus 3 equals 9 molecules of water less in the cell. The colloidal, the red, content contracts from the cell wall and gets smaller and smaller under the microscope. The cell loses its red color. Adding fresh water instead of the saturated solution of kitchen salt to the whole arrangement, the process reverses. And as we see in between, the process of, let me put it like that, recovering of the cells has gone on quite far, and as we see, nearly all the red cell plasma has expanded to its former size. The bear here is a little bit still white, but all over the place. Now here's the end of the sample already. All over the place, the cell plasma has expanded and is now filling out the whole cell.